What is energy? How do you know if something has energy? Finished? Nice. I just leave it in one big stack on that desk right there, and I'll deal with it. What is energy? How do you know if something has energy? Anybody? Emma, was that a hand? No. Okay, that was not a hand. Sire. Sorry? Excitement in particles. How do you know if a particle is excited? How fast it's moving. So the faster, so you're suggesting, William, I moved them all to the front. I'll just leave them on the desk next to David. So you're suggesting that if a particle is moving fast, it's got a lot of energy. So if a particle is moving slowly, it has less energy. Okay. So the faster something's moving, the more energy it has. Certainly possible. Actually, you're right. Yeah, that's a thing. What else? How else do you know if something has energy? Yeah. Heat. So you're suggesting that hotter things have more energy. The cooler something is, the less energy it has. Okay? What else? So, okay. Sorry? Dang it, you do that again. I don't quite hear it, and then you deny ever having said anything. Okay, so let's a few things. Energy is, or how you know something has energy. It moves fast. If it's hot. How else? How do you know if a person has energy? If you say that is an energetic individual, yes, they could be moving. Yeah, they could be warm. They could also be. Think about the person in your class, people in your class that are typically higher energy people. They might what, sorry? Okay, what does that look like? They're hyper. What does hyper look like? Bouncing off the wall, so there's lots of movement there. Those people are often also what? Talkative, they're loud. What do you mean? That's not necessarily reflective of how much energy. It's not necessarily a measure of energy. I've never thought about that way. I'm not gonna. I guess I can't say no. I don't know. That one I can't speak to. But generally speaking, if you're looking at objects that have energy, they're moving fast, they're warm. Like there's an increased temperature there. They could be loud. As it relates to this unit, how we're going to define energy is this. We're going to say energy is the ability to do work. And we still haven't defined work, but I mean, your understanding of work and the physics definition of work are going to be different. I know that already. But as a place to start, this is a decent one. Energy is the ability to do work. The people who are moving fast, the people who are bouncing off the walls, the things that are hotter than colder, the things that are louder than not. These are all the things that have the ability to do more work than the cold, the quiet, the moving slow. So energy is the ability to do work, and it's at this stage important to recognize, does energy, like with every concept we've looked at so far, does energy have a direction associated with it, or is it just a quantity that someone or something possesses? It's just a quantity. So that makes energy what kind of mathematical object? No, so yes, not the vector. The not vector is a scalar. It doesn't make sense to talk about energy as having a direction. Energy is. Either you have it or you don't. You don't have it in any particular direction. You might be moving in a particular direction, but that has no bearing, the direction you're moving in has no bearing on how much energy you have. It's just how quick. So there's two main types of energy that we typically look at, either kinetic or potential, and everything is kinetic energy, and then we'll break it down further. If we're talking about heat, we will talk about heat in this unit. Heat is just the rapid movement of particles, so kinetic energy. Electricity is just the movement of electrons through a conductor, so kinetic energy. Loudness is just the rapid movement of air molecules that I'm generating that you're hearing, moving the little hairs in your ear back and forth. Your brain turns my voice into a sound. It's just movement. So much of what we look at is kinetic energy. And when we talk about kinetic energy of a larger scale, we're going to use the equation that you would have looked at last year. Kinetic energy is the energy that comes from motion. Anything that's moving has it. The equation for it is what? Do you recall? Sorry? I heard whispering. Yulia, what's the equation for 1/2 times m times v squared? You betcha. 1/2 mv squared. And in Science 10, we just give you this. There is actually good reasons for where this comes from that I can't tell you about or show you about until you've taken some calculus. But there is a relationship between energy and other concepts that are related to each other through calculus. This is all right here. We are now in this section of the formula sheet, and because it's May 30th, this is probably where we're going to end. If I can get into some circuits, I will, but this is probably going to be it. So EK, or sometimes it's called KE. Again, you need both letters there. It doesn't really matter what order they're in. It's either energy kinetic or kinetic energy. That is equal to 1/2 mv squared. Now, mass is measured in what units? Mass has always been measured in kilograms. And velocity is measured in meters per second. So if I'm taking my mass in kilograms and I'm multiplying it by a velocity squared, then the units are just going to be kilograms, and then I'm going to square these units. Meters squared per second squared. But those are really quite cumbersome. Who cares about a kilogram meter squared per second squared? We're going to take that and we're going to make it something more useful. It's like the newtons, or the newtons. The kilogram meter per second squared. We want to get rid of the kilogram meter per second squared. We called it a newton. Those are the units of force, and we gave it the name of the guy responsible for a ton of work in the area of forces and dynamics. Similarly, we take the kilogram meter squared per second squared and we give it a name. We name it after a different guy. Does anyone remember what you would have called it last year? Energy is measured in joules. Or the joule. A joule or joules. Named after, I believe he was a British physicist. Well, the first two names are James Prescott, and I don't know if anything sounds more British than that. James Prescott Joule is who this unit is named after. And you would have looked at this last year. A typical question that you would have been given in grade 10 from Mr. Radney or Mr. O or Mr. Easton. A 5 kilogram object is moving at 7 meters per second. What is its kinetic energy? Well, kinetic energy, KE, is just 1/2 mv squared, just like everything we've done. Write out the equation and then plug in your values. It's be 1/2 times 5 times the velocity, and we want to make sure we square that. So 7 squared is 49. Half of 5 is 2.5, so 2.5 times 49. I don't expect any of you to be able to do that in your head, but 2.5 times 49 is 122.5 joules, something you would have done ad nauseum last year. Not an overly difficult calculation to do. But really, this is, it's kind of it's completely abstract. It's kind of meaningless. It's not like you're moving down the hallway, running down the hallway, You see someone big, but they're slowly moving down the hallway. And it's not like it's easy to say to yourself, okay, well, this is how I would quantify that energy. We kind of do this anyway. You look at a really small, kind of hyperactive, bouncy person, you say that person has a lot of energy. But we don't often look at the really big, lumbering person and say that person also has a lot of energy, even though they do. Kinetic energy is dependent on your mass and how quickly you're moving. So a really, really big object moving slowly is still going to have a lot of kinetic energy. Just like when we were dealing with inertia last chapter, and the question I kept asking you is, how much would this hurt you? That's a decent example for reflecting on momentum. It's a decent example for reflecting on energy. If this object hit you, how much would it hurt? So you can have really small objects moving very quickly. The hyperactive, my son, running at you at full speed could hurt if he hits you. Fujimura, walking even slowly, could hurt you. And so it's a decent way to think about energy. Would the object hurt you if it hits you? So that's kinetic energy, and kinetic energy is a bunch of uses we're going to look at. But there's also potential energy, and then depending on what causes it, you get a bunch of different kinds of potential energy. Potential energy is energy that's stored within an object. It has the potential to use energy at a later time. When you think about potential energy, we think about things like, falling objects. If the object is sitting on my desk, does it have a lot of potential to do anything? No, generally not. If I raise the object, could you foresee a circumstance at some point in the future where this object could do something? Yeah, all I have to do is let it go. But if I take this object and say, if you had to suggest whether this object had more energy than this object, which object has the potential to do more? This placement or this placement, or are they the same? You're suggesting that this has more of an opportunity to do work than this one does. Why, Colvin? How? Why? Because it has a longer distance to fall. Even though materially speaking, I haven't done anything different. I mean, my arm's getting heavy, so the object's slowly dropping. But, I mean, this object and this object are the same altitude above the ground, like the ground. We're up on the 3rd floor. But if you isolate yourself to just the classroom, yeah, this one has more potential than this one, just because it has a further distance below it, which is kind of abstract. I mean, it makes sense, but it's, even in and of itself, it's pretty abstract. I could do the same thing with the rubber band. The rubber band here, if I just held the rubber band at Kai, should Kai fear the rubber band? No. But if I pull the rubber band and I point it at Kai, should Kai fear the rubber band a little more than he did before? Yeah, probably. Even though nothing's actually happened. I'm not going to shoot it at you, Kai. I'm taking it away from pointing it at your face. Even though nothing's actually happened, there's a potential there. There is a chance of something occurring. So there's all sorts of ways that we talk about potential energy, and that's really it. It's, what are the chances that something could happen? If they're anything other than zero, there's potential energy there. So we're going to concentrate on 2 types. The first one's going to be gravitational, which, again, you looked at last year and you already have an understanding of now. There's gravitational potential energy, and there's another kind. The one I just demonstrated is elastic potential. There are other kinds that we're not going to look at that we'll save for either grade 12 or a whole nother course. There's electric potential energy. There's chemical potential energy. Electric we'll save for physics 12. Chemical actually gets dealt with in a bunch of courses. Chemical potential energy gets dealt with in chemistry. Chemical potential energy also gets dealt with in foods. Chemical potential energy also gets dealt with in, is it planning? Wherever you learn about nutrition, is it just a discussion on chemical potential energy? If you take in more chemical potential energy than your body has use for, you gain weight. If you use more chemical potential energy than your body's taking in, you will lose weight. So nutrition is a part of it too. Chemical gets dealt with everywhere. But we'll start with gravitational. Gravitational is due to having a height above some reference point. And the crummy part of saying some reference point is, and again, the thing that students don't like about this is you get to choose. Your reference. And there are better ones than other ones, but there are really no wrong reference points. Colden, when I held the pen over here, what was your reference point? Yeah, the table, because that's what was beneath it. When I hold it over here, what was your reference point? The ground. I mean, is one any better than the other? Could me holding it over here, could your reference still have been the table? Yeah, it could have. But what happens when the pen goes below the table? Now you're going to have negative potential energy, which doesn't make a lot of sense, but works. Like, there's no reason why the math couldn't work for it. You're just choosing a reference that says if the table is what we're going to call 0, then below the table we're at a negative potential energy, which is weird, but it's going to be something that you're going to have to deal with in Physics 12 when you guys talk about orbital potential energies, which we're not going to do here because orbits are beyond what we're going to look at. Is there another reference point we could have used that would make sense for this pen? We've got the pen here over the desk. I've got it over the floor. Is there a more absolute reference point we could use? Yeah, Sire. Oh, where my hand is? Sure, you could use that because in this case, it would be this. They'd have the same if I'm the reference point. So let's hold it here. I'm over the desk. So you're suggesting the desk. Over here, it's the ground, the floor. So it's the floor. If I keep this thing at the same height and I go out the window, then the reference is going to be the ground, 3 stories down, right? And so there is always kind of an absolute, what you would call the most 0. Often we talk about the most 0 being the ground, but again, you get to choose your reference, just like when we were doing dynamics. You guys got to choose positive and negative based on what made most sense in the question. When you're dealing with potential energies, you get to choose what 0 makes the most sense, and I'll show you what I mean by this, but given the question that you're looking at. So, I mean, you did this last year, but I'll just kind of go about re-emphasizing it. If I hold these 2 objects at the same height, well, we can argue. This one is above the desk, this one's above the ground. Which one of these is going to have the more gravitational potential energy? Over the desk or over the ground? Over the ground, it's got further to fall. Okay, cool. What if I did the same thing with these 2 objects? Which one's going to have the larger potential energy? Which one can do more work? Or which one would hurt you more if it hit you? Probably the coffee cup. Highlighter bouncing off your head versus my stainless steel. You don't know how much coffee's in here. I might have no coffee in here. I might be full of coffee. Either way, it's gonna, if it hits you in the head, if I drop this on you, this one would hurt more than this one. So this one's got more potential energy. So potential energy, gravitational potential energy depends on a few things. It depends on the mass. It depends on your height above the ground. Oops, I shouldn't write them in that order because that's not the order you're used to seeing them in. It depends on your mass. It depends on your height above whatever your reference is. This is above the reference. ENCE. And it also depends on what? If I took these same two objects and I held them above your head, and then I were to somehow teleport us to the moon and held them above your head while we both held our breath and froze to death slowly, in which circumstance would you expect to be hurt more by the things that hit your head? Colin. Here or on the moon? Here. Why is here going to be more concerning than the moon? There's a stronger gravity. These things are going to be moving quicker when they hit you on the head if I'm holding them above you, both here and somehow on the moon. So gravitational potential energy depends on the mass of the objects. It depends on the height you are above whatever reference you've chosen, and it depends on the gravity wherever you're located. It's not always written as PEG. Sometimes it's written as EPG. Sometimes it's written as U. Why? I don't know. Sometimes it's written as EU, but you'll see all these notations. But potential energy due to gravity is equal to the mass times the gravity times where you are times the height above whatever you've chosen your reference to be. And if we look at the units on this thing, the units of mass are still kilograms. The units of height above something are meters. And what are the units for G? Meters per second squared, because it's an acceleration. So this is going to be meters per second squared. And if we put all those units together, we're going to get kilograms times meter per second squared times meters. Oh, look. That's kilogram meters squared per second squared. Those are the exact same units we had before. Even though they're measuring something, an entirely different concept, this one is all dependent on how fast you're moving. This is potential. You're not moving yet. You're just above the ground. The units are the same. And so conceptually, these must be equivalent, both energy. So then this is also going to be measured in joules. There's an eerie consistency there. And another calculation that you would have done a bunch of times in grade 10, potential energy is equal to mgh. If you have a 10 kilogram object at rest at a height of 12 meters, what's the potential energy of that object? Well, you've got a 10 kilogram object. If it doesn't specify, you can assume you're above the ground. And you're 12 meters up. Stop me if you've got questions or if things are not. Yeah, those are squareds. Yes, Jack? You bet. You multiply these three values together, and again, I expect you to be able to do that with your calculator, so I'll just give you the value. That's 1,176 joules of potential energy. If we dropped this 10 kilogram object from a height of 12 meters above you, it would have that much energy when it struck you in the head, which would suck, presumably. It would be worse than the 5 kilogram object moving at 7 meters per second, substantially worse, because it's moving, well, it will be moving a lot quicker. Questions, comments, concerns so far? This is stuff you've done already, perhaps in grade 10. So when you're ready, flip the page. Look at the next one. Some of you guys would have done this with your grade 10 teacher. Some of you may have not. Hands up if you looked at elastic potential energy in Science 10. You had Mr. O? You had Radnai. Radnai did elastic potential. Cool.
We did like all of the...
This one's not in the textbook, though, and I know Mr. Radnai loves the textbook. Okay. I don't either. I know Mr. O does it. I'm pretty sure Mr. Easton doesn't. I know O does. I don't know about Radnai. Okay, elastic potential energy. Elastic potential energy is due to energy stored in elastic material. I mean, we can demonstrate this a bunch of different ways. If I took this elastic, hold on. If I took this elastic material, talk about their differences. Which one of these is, Which one of these is more intimidating to you at this stage? I think this one's more intimidating. Okay? What if I pulled them all back and pointed them at you? Why is this one more intimidating? Is it bigger? Okay? What if I pulled them all back and pointed them at you? Which one would concern you more? Still this one? Why? It's going to whip at you. Okay? The umpiness of a spring is dependent on what? Two things. At this stage, are any of you fearful of any three of these? As they sit in front of you, none of you should be scared of any of these three. Because what makes a spring scary? The stretch and what else? Not just how much you've stretched it, but how hard it is to stretch. If you see me do a ton of work to barely get this thing stretched, that should concern you. If I put all of my energy, all of my ability into stretching a spring, that should concern you about the spring. So this one is a little bit more difficult than this one, but I can stretch this one further. So which one's more important, how much I can stretch it, or how stretchy it is? David, would you do me a favor? Can you come grab that end of the spring and just go for a walk? It's not overly difficult. Like, David's having no issue walking backwards. Yeah, that's good. You're good. Thank you. No. Stay there. Stay where you were. You can still hear me. They just can't see you. David is past. He's like a third of the way down the cork board. So this thing is substantially more stretched than it was before. But it was pretty easy to stretch. Right? Yeah? Like, that wasn't difficult for you to make that walk? But yeah, I'm a little concerned. Let go. Because all of that walking loaded this thing with a bunch of potential energy, such that when he let it go, I'm grateful it was my foot and not any other part of me, but it came flying back pretty quickly. So, which of these is the concerning part? Kale, welcome back. Your test can go on the desk up here, and the booklet you need is on the desk in front of David. The whole stack right there, yeah. So what's the issue here? The elastic potential energy is stored in elastic material, and it's caused by the compression or the expansion, the stretch of the spring. Now, some of the springs that you might work with, especially if you're in automotive, are generally compressed. Shocks, from my understanding at least, you compress them to put them in there, but not their whole way. Like, there's some give up and down. You want the car to be able to rest upon them and have space to move either way. Car shocks should concern you. One of the worst things that I had to deal with when I was a first aid instructor, or not an instructor, a first aid, attendant here at school, was Mr. Wimmer. One day after school was trying to deal with a car shock, and he got his hand slammed in it. And Mr. Wimmer's a tough dude. And I watched Mr. Wimmer go into medical shock, which, given his rugby injuries, given his automotive history, was rather concerning to me. I watched Mr. Wimmer turn white and then turn gray and go into medical shock, which was a big deal. There's a lot of potential for a lot of damage to be done when you're dealing with springs. Spring potential energy is given to us by the K value. The harder the thing is to stretch, the more potential energy it's going to have. It's given by the extension of the spring, also deeply concerning. But Kx was just the force, so that's not going to be, like, we can't have the force being equivalent to potential energy. So we have to do some stuff to these two concepts, and we're going to do the same things to these concepts that we did to motion. We're going to take the half, multiply it out front, and we have to square the x. And that's going to be our expression for spring potential. Why that is, that's a question for a calculus teacher when you're actually taking calculus. But this is the expression that we use for spring potential. Now, if we take a look at the units for this, I'm not going to necessarily expect you to remember, though, I could because you just wrote the test. The units for K were newtons per meter, the force required per meter of extension, and the units on X were meters. So if I square X, it's going to be meters squared. And if I'm multiplying these things together, if I have newtons per meter times meters squared, what I'm going to get is a unit of, that's going to cancel with that guy, and I'm going to get newtons times meters. Well, that's interesting. What are the units on newtons? Like, so we converted something into newtons because newtons was easier to deal with. What was the alternative unit we had for the newton? It was something related to kilograms. Kilograms times meters divided by seconds squared, because F equals ma. Mass times an acceleration. Well, I'm going to multiply that by a meter again, and oh, look, we have a kilogram meters squared per second squared, which is also a joule. Yet again, another equivalent expression. Totally different scenario. We've got spring constants and extensions, but when you look at the units, they are equivalent to the units on kinetic energy. They're equivalent to the units on gravitational potential energy. So we can lump them all together and say, you know what, this is a joule. That should be weird to you. But on a Friday morning, we're tired, and maybe that's not quite so weird. So then the question asks, what is the potential energy in a spring with a spring constant of 4,680 newtons per meter that has been expanded by 15 centimeters? That's in meters, so this thing needs to be in meters as well. How do I go from 15 centimeters into meters? Divided by 100. You say it like I've asked you that a lot, Kai. See you later, Colden. Good luck. Should I tell them all where you're going? Or is that a lot of pressure? Okay, well then everyone wish Colden good luck on his N test. Good luck, Colden. If we divide that by 100, I get 0.15 meters. And so now that's the expression that we're going to put into our spring potential equation. So potential energy for the spring is going to equal 1/2 kx squared. So now I'm going to put these values in here. It's going to be 1/2. Our k value is 4,680 times by 0.15, and we got to make sure we square that. So what's the potential energy there in the spring? I will give you that value. That is not an overly difficult one to do, though the key here is going to be to remember squaring this thing. It's not just kx, it's 1/2 kx squared. And again, all of this is on your formula sheet. There's nothing to memorize. The value here is 52.65 joules. So as far as the three examples go, The scariest one is the 10 kilogram object held 12 meters above you, which, I mean, that's really far. That's 30 feet above your head. Nope, that's 40 feet above your head. That's a 10 kilogram object falling from a height of 4 stories. That should be very concerning. Comments, questions, concerns on what we've done so far? This is basically like a week of Science 10, condensed into about 20 minutes. Okay, so that's gravitational potential energy, spring potential energy, and kinetic energy. Stuff that you've looked at already. What's work?
Sitting next to the
How do you know if you've done work? Now, in English, we use this word work to represent a bunch of different things. I mean, lots of you have jobs. If I take this thing and I move it over there, have I done work? I mean, could you have a mindless job that required you to lift the thing from over there and move it over here? Anyone ever had a job like that? I have. Generally, it's not a little plastic container full of masses, but you're working on a berry farm. Lots of jobs are pick the berries, put the berries, weigh the berries, move them over there. You're just taking something and you're moving them. So what part of that is actually work? What is required to call it work? No. Believe it or not, we're not going to connect it. At what point have I actually done work? If that's my job, I'm working on a berry farm. I did for 7 years. My job was to work on the berry farm. How do you know if work has actually been done working on a berry farm? Pretend this is a berry bush. Work is done if the berries in the bush make it to where? Sorry? Okay, so there it's on the bush. I pick it and I place it in the bin. Some work has been done. The job's not over yet though. Because now what do I have to do to these objects? I pick all my berries. They were on the bush. They're no longer on the bush. Now I have to go and I have to take, they gotta be sold, right? So I have to take them out of the field. I have to give them to someone to weigh, and I have to put them on the field. Like the most fundamental jobs we do involve taking an object from one place and moving it to another place. And that's going to be part of our definition here for work. Work is dependent on actually moving something somewhere. If you haven't done any moving, you haven't done any work. Which is a little bit different than what we think about, right? We often think about the fact that you're tired at the end of something, so therefore I must have done work. But let's say Irem. Irem's the berry picker. Here are the berries on the bush. And for some reason, Irem has a buddy whose job it is to hold the box. Pick the berries. My life for 7 years. Pick the berries. She picks the berries. Yep, keep going. I'm holding the box. When your hands get full, you can put the berries in the box. That's my job, right? I'm just standing here helping you. I'm holding the thing, making your life a little bit easier. At this stage, who's the only one that's done any work? Irem. Irem's the only one that's done anything. Even though if you were tasked with standing here and holding this, it feels like I'm doing work. I mean, you've all done something stupid like this. Stand there and held something heavy because someone else asked you to do it. And it sure feels like I'm doing work, but according to this definition, have I done any work? No. I don't do any work until this thing goes somewhere. I take it to the truck, truck carries it to the store, and gets it. Unless you actually do some movement, no work has actually been done. So we need that movement in there. And then to connect it to this idea of, I mean, you're not going to move anything unless you act on it with some sort of force. And so it seems a little bit arbitrary, but we're going to take these two things and We're just going to multiply them together. Well, let's look at what multiplying a force and a distance does. If I take a force and I multiply a distance, what are those units? Well, force is measured in newtons. Distances are measured in meters. That looks an awfully lot like what we did up here. Newtons are just going to be kilogram meter per second squared. Meters are still just meters. So I'm going to get a kilogram meters squared per second squared. That looks an awful lot like what we've written down 3 times already. We call a kilogram meter squared per second squared a joule, which means actually doing work is equivalent to what? A joule means you're expending energy. That's interesting. Yep, I could have been. But if I'm just holding the berries, D is 0, I don't have the meters to multiply by, it wouldn't work out. You actually, if for it to be you holding the berries, you actually have to move them somewhere. Otherwise, it's just the potential of doing work, which isn't work. If your boss walked up to you and you said, I could do work if you wanted me to, and the boss would say, I want you to, that's why I hired you. I'm paying you to do work, not to just stand around and show me that you could do work later. If you get caught by the boss standing around potentially doing work, you're going to get in a lot of trouble. You actually have to go ahead and do something. So work, we can have 2 definitions. Let's go back and define it now. There's 2 ways that we can define it. We can talk about work as being a force acting over a distance. Or we could talk about work being using up energy. Energy being the KE or the PE that we've talked about before. Hey, what's up? For Raina, go get your present. Yeah. Okay. So, more examples of the same. The formula is not difficult. If we're talking about work, work is just a force. At this stage, work is just a force acting times a distance. Now, here's an interesting thought. Because work is just energy, it should be a what kind of mathematical object? If work is measured in joules, should it be a scalar or a vector? Well, everything else measured in joules has been a scalar up to this point, right? Energy, kinetic energy, direction doesn't matter. Potential energy, there is no direction because nothing's happened yet. So this is interesting. Everything up to this point that's been measured in joules has been a scalar. So then, therefore, this thing has to be a scalar too. But forces and displacements are both vectors. So then how can you take 2 vectors and multiply them together and get a scalar? Which perhaps you haven't thought about. Sometimes the more math... Sorry? It's kind of like a negative times a negative gives you something positive. A vector times a vector, there's actually 2 ways, and you'll learn this as you go off into math. There's actually 2 ways you can multiply something together. You can multiply something together using that symbol, or you can multiply something together using that symbol. And up to this point in your mathematical career, those have been the same symbol. They're not anymore. The dot and the X are different kinds of multiplication. This is called dot multiplying, and this is called cross multiply. And depending on what you do, one of these will give you a scalar and one of them will give you a vector. When you've got this, we're dot multiplying, and don't worry about what that means, you'll get there one day, but we're using this symbol. Hey, Mr. Morrison, what's going on?
Can I borrow your razors for some set fraction?
They're broken.
Oh no!
But
That's too bad.
yeah, they unglued.
Oh, that's okay. I'll just do the diffraction rating.
I would happily, but
I'll get Christy to fix it next week. I'll just do I already got the diffraction grading set up.
Okay.
That's fine.
Yeah, I have to chip off the epoxy. It's not a big enough surface. Sorry. Otherwise, yes.
Okay.
Yes. But for which? Yeah. Right here. I think it's plugged in on the other side. No, or it's this one. One of those two. Okay, back to this. So we're gonna multiply these things together in such a way that we get a scalar. You gotta do what you gotta do. And we'll do a couple examples of this, and you likely won't have any homework, but we'll see what happens. Here we go. Examples. If a student pushes a box with a force of 80 newtons along a surface that is 3.5 meters long, how much work has the student done? Well, the work that the student has done is going to be equal to the force applied by the student times the distance over which the student has pushed. Or how has the student displaced the thing? Just because it's hiding behind the water bottle doesn't mean I don't know it's not there. So the force is 80 newtons. The displacement of the object is 3.5 meters. So how much work has the student done? We could draw this picture out. Let's free body diagram this thing, because why the heck not? There's an applied force to the right. There's an FG, there's an FN. And at this stage, that's all we've got. Are FG and FN doing any work in this question? Is the box moving in either of those directions? No. So FG, the gravity's not doing any work. The normal force isn't doing any work. It's just the student pushing. You multiply those values together, and you're going to get 280 joules. So that's the work the student has done. What about the work done by friction? Let's say in this same scenario, there's friction acting on the block. Friction's pushing back now. Is friction doing any work? Yeah, it is. Why? Because I'm asking the question, your gut says yes? The box is moving left, right? The box is being pushed to the right. Friction is acting to the left. So you've got a force acting in the same directional plane that the box is moving in. And so yeah, friction is going to do work. But let's look at this. I've got forces acting in different directions. So now we need to call a direction positive. Let's call the applied force the positive direction. So now when I go ahead and I punch this thing in here, I'd say, okay, well, if I want to figure out the work done by friction, friction is a force times the distance. What's the force? Or force times the displacement. What's the force now? No, the work done, but we want the work done by friction. So what's the frictional force acting on this object? It's 8, but it's backwards. So we're not going to put 8, we're going to put negative 8. And it's still being displaced a positive 3.5 meters. So what is the work being done by friction? Well, 8 times 3.5 is going to be 28. And one of those values was negative, so this whole thing is going to be negative. What does it mean? But work doesn't have a direction, so what does it mean? Yeah, just put the whole thing on that stack right there. Welcome back. What does it mean for work done to be negative? What does friction do to the box? Slows it down. So it's pulling energy out of the box. What does friction turn that energy into? What is the effect of friction on moving objects beyond just slowing them down? Here's a friction exercise for you. I want you to take your hands and I want you to rub them together until you can, okay. They're going to get hot, right? You rub your hands together, and eventually it's going to become uncomfortable. Eventually you're going to start burning your hands. If you've never done this, do this. Demonstrate this. Heat's being produced and a sound is being produced. So that negative symbol represents energy being drained from the object and depending on how it's being drained, different forms of energy will result. In this case, this leaves as heat, mostly heat, and sound. The vast majority of it leaves as heat, heating up the object. You guys don't necessarily experience this because it's usually the object you don't heat up when you slide the object along the ground. So it's not something we think about because it's not happening to you. Human beings are inherently selfish. But that object's heating up. She took the time to feel the object. So we've got work done by the student, we've got work being done by friction. What is the overall amount of work done? Or the net work being done? How did we find the net when we were talking about forces? The sum of them. So if you want net work net is just equal to the sum of all of the works. So in this case, it's going to be 280 minus 28. What is the net work done? Well, 280 minus 28 is 252 joules. But is there another way to do this? Yeah, you bet there is. If I look at this net work, or the sum of all of the works, this is just the sum of all of the forces times distances. There's only one distance happening here, but there's a bunch of forces. So this could actually be written as the sum of the forces times the displacement, and the sum of the forces is just the net force times the distance acting. Net force is just the sum of all those forces. So if I added those forces together, I've got an 80 Newton force to the right, and I've got an 8 Newton force to the left. I could just rewrite this and say, okay, well, my net force is just going to be 80 minus 8 times the displacement of the box. 80 minus 8 is 72 times 3.5. And if I'm not mistaken, 72 times 3.5, just so you know I'm not screwing with the numbers, it's 252. So there's all sorts of ways to look at these same concepts. Welcome to Work, Power, and Energy. This is where we will end our lesson for today. I am not going to give you any homework today. You can enjoy your weekend homework lists. If I've ticked any of you off in the last couple days, I will be downstairs during lunch for the balloon throwing fundraiser. I encourage you to come spend your loonies and toonies and throw water balloons at me if it would make you feel better about any portion of the last several weeks. It's it's for a good cause apparently, so I'll be down there. When the bell goes, you may also go have a super great day. Yeah, next Friday, sure.